Welcome back to Carneades.org. Today we're going to be looking at the philosophy of outer space, Part 2, Cosmology. Now, this is Part 2 of our giant video on the philosophy of outer space. This one is focused on cosmology. Stay tuned for Part 3, as well as the full video from beginning to end coming out soon. Next, we're going to dive into cosmology. So, cosmology is the science of the universe. As we move outside of the asteroid belt, we shift from the Fermi paradox to the philosophy of cosmology, the science of the universe. Cosmology is quite a complex field, and the goal of this part of the video is not to explain all of cosmology, or even to explain all of the philosophy of cosmology, merely to give an introduction to the subject and to talk through some crucial philosophical issues that arise. Now, cosmology has its biggest impact for philosophy in the areas of philosophy of science. Are the methods of cosmology really science or just pseudoscience, something more like philosophy itself? Philosophy of religion, how did the universe begin and how likely was it to begin? And metaphysics, are there multiple universes that exist, and is a real infinity actually possible? We'll look at all of these questions here. But first, a little bit of background. Cosmologists observe the universe by looking at the light and other electromagnetic waves that reach our planet. These allow us to look both far in terms of distance as well as backwards in terms of time, because light takes time to reach us. The further away something is, the further back in time we are looking. Cosmologists then develop models for the universe and see if the observations that we see match the predictions of those models. Sometimes cosmologists posit unobserved entities like dark matter or dark energy to explain phenomena that don't quite fit their model or observations. Now, cosmology is a particularly unique field for a range of reasons. Most subjects of scientific inquiry are the kinds of things that can be experimented on. They have multiple things that they can study and survey using statistics to increase our level of confidence. Cosmology is unique because there's only one universe that we can observe, and the vast majority of it is something we cannot run any experiments on. And we're only observing from one point in space and from a very limited point in time. There is so much space and there is so much time, and we only have a very, very small sample. The current paradigm for cosmology is the Standard Model, which uses what we observe about gravity and other forces locally to extrapolate conclusions about what the universe is doing as a whole. This model requires assuming the existence of dark matter and dark energy to explain why we don't observe as much matter or energy in the universe as we would expect. In order to do cosmology, we need to make some big assumptions. Specifically, we need to assume something called the cosmological principle. We need to assume that the part of the universe that we can interact with is a fair sample of the entire universe. In other words, that the laws of the universe in general make up the universe in other parts is the same as what we see here. This applies to both experiments done on Earth, as well as the behavior of cosmic objects within the observable universe being the same as those outside of the observable universe. Cosmologists need to do this to do cosmology, and at all, since we cannot actually test the conditions on the other side of the universe. As we will see, this raises some epistemic concerns. With that, let's talk about some of the problems with cosmology. Now, there are a lot of issues with the Standard Model that signify we might be due for a paradigm shift. Dark matter and dark energy are some of them. These are things that, particularly dark matter, is something we cannot observe, but must be there to make our theories work. These have a clear parallel in the shift away from classical mechanics to what we now include as our paradigm around physics. Our classical theories could not explain the perihelion in Mercury's orbit. Initially, instead of changing our paradigm away from classical mechanics, we posited an unobserved planet named Vulcan that was between Mercury and the Sun. It turned out there was never such a planet. Our theories were wrong. Similarly, needing to posit things like large amounts of dark energy or dark matter in the universe to make our equations work doesn't necessarily, but may indicate that the problem isn't that there's a bunch of stuff that we can't observe, but that our equations are actually wrong. Now, falsifiability. One of the biggest issues with cosmology from a philosophy of science standpoint is that it isn't really science. Karl Popper argued that the claims of science must be falsifiable. However, the claims of cosmology, particularly the cosmological principles themselves, are not falsifiable. We need to assume that the universe is uniform at a sufficiently large scale to draw conclusions about faraway locations, but we can never actually go to those locations to test if these conclusions are true. If they're false, we can't do cosmology. If other parts of the universe look drastically different, follow very different laws from what we see on Earth, we can't really test that, and we can't test those other parts of the universe to figure out what laws they follow. One might suspect that it would be strange for our corner of the universe to be different, statistically speaking. Why is the one place we can observe from look different? The odds of our specific corner of the universe being one way and everywhere else being another are very low. However, there are a few problems with this framing. First, as any statistician will tell you, even if you have a truly random sample, a random sample of one place is insufficient to be representative of the whole. Second, even if most of the universe acts like the area around Earth, it doesn't imply that it all does. Even if it's unlikely that we are in a weird pocket of the universe, it doesn't mean that those pockets don't exist. Third, it is possible that the universe is not at all uniform, that there is no normal part, that every part has its own rules and its own laws. And it's not strange that our part has one set of rules, because every part has drastically different rules. Cosmologists commit the fallacy of necessitation here. They assume these principles because they're the only way to do cosmology. If they were false, we couldn't know anything about the other parts of the universe, since they might follow different laws. Beyond questions of falsifiability, cosmology suffers from the problem of induction, but in reverse. For any science to function, we must assume that the future is like the past. In other words, that our observations in the past will continue to hold in the future. Cosmologists must assume an inverse principle, that the past behaved like the present. Cosmologists draw conclusions about the past by looking at very far away objects, because light takes us a long time to reach us. The further away they look, the further back into the past they claim they can observe. However, often they are observing much further into the past than humans have ever existed or been able to observe things. However, just as this would only work if our location in space follows the same rules as other locations, this also only works if the rules have never changed in the past. If the laws of physics were different in the past, then all of the conclusions we think we can draw from looking at light that is just now arriving might be invalid, since that light might not be as old as we think it is, or it might simply be behaving under different rules because other parts of the galaxy might have different rules from what we have now, or other points in time might have had different rules. Our interpretation might be based on laws which did not apply when it was created. The problem is that there's no way to prove this true without time travel of some kind. It could be that the laws of the universe changed drastically at some point in the past. In fact, under current theories, cosmologists must assume something called cosmic inflation, which requires objects moving faster than the speed of light, which would break one of the rules that they need to assume in order to conclude it. Now, sometimes cosmologists argue that these theories can at least be verified by looking at something called the cosmic microwave background radiation, the radiation that we see from the first moment that the universe became transparent. The problem is that this still faces issues of underdetermination. While specific theories can be supported or not given a certain paradigm, the entire paradigm itself is much harder to verify, since there are many other paradigms that could explain the same observations. And without the ability to go far into the universe to test these theories empirically, at a certain point we're overfitting the theories to the limited data we have. If the only thing we really have to test things again is this cosmic microwave background radiation, then at a certain point we're going to create theories based around that to overfit the data, and perhaps not actually be doing anything that's testable because we don't have new data that's coming in. Very quickly as an aside on philosophy of science versus science. So, before a bunch of cosmologists get too frustrated in the comments, it's important to note and remember that there's a difference between science and philosophy of science. It is science's job to use the scientific method to test claims based on that method. It is the job of philosophy of science to determine which situations the scientific method can be validly applied to and whether or not a given situation is actually using the scientific method appropriately. Philosophy invented science, and it's the job of philosophers to determine what is and is not science. Because science doesn't study knowledge, philosophy does. Science doesn't study truth, philosophy does. Science doesn't study the scientific method itself, philosophy does. Therefore, it's fully within the purview of philosophy to question whether or not cosmology is really a science. Note that philosophers are not questioning, does cosmology say X, but rather, are claims made by cosmology justified? You might think of this like the difference between philosophy of religion and theology. It's the job of theologists to determine what a holy book says. It's the job of philosophers to determine if the claim that whatever the holy book says is true is actually justified. Philosophy is the discipline in which other disciplines swim. This is why everyone still gets PhDs, doctorates in philosophy, because everything used to be philosophy. All right, moving on. The Big Bang. In the beginning. So, if we do allow these underpinning assumptions, cosmology can provide us with hypotheses about the origins of the universe, sometimes called the Big Bang. This has philosophical implications as it approaches an answer to the question of how the universe began, what the limits of our knowledge are, and much more. We will very briefly and simply explain the current timeline according to cosmologists. Now, the first question is an epistemic one. How can we possibly claim to know what the universe looked like when it started, which, according to scientists, was over 13 billion years ago, when humans can't even agree on the facts of our own planet, even a short time in the past? Is evolution true? Did we really land on the moon? Who did we say was supposed to pick up the kids this afternoon? Etc. The first thing to understand is that this model is that light takes time to get somewhere. Light takes just over 8 minutes to get from the sun to the Earth. To get from here to Saturn, it takes just under an hour and a half. This means that the further away you look, the further in the past you're looking. Because the distances in space are so large, this means that you can actually look a long way into the past. Light from Proxima Centauri, the nearest solar system, is from around 4 years ago, meaning we are seeing it as it was 4 years ago. Light from the center of the Milky Way is around 26,000 years old. So we are observing the center of the galaxy as it was about the time that some of the early instances of human pottery were created. The nearest small galaxy, the large Magellanic Cloud, is 179,000 light years away, meaning we're looking at it as it was when humans first started wearing clothes. We're seeing the nearest large galaxy, the Andromeda Galaxy, as it was 2.5 million years ago, how it was before we had gone from prokaryotes to eukaryotes. Perhaps this is an explanation of the Fermi paradox right here. Perhaps there are many other civilizations that are existing in other galaxies, but we just haven't gotten the message yet because it takes so long for light to travel from those galaxies here. Okay, so we can look back in time by looking really long distances. But how do we tell what those galaxies are doing? Whether or not they are moving away from us or towards us, etc. Cosmologists use something called the Doppler effect. Now, you've likely experienced the Doppler effect with an ambulance. As the siren gets closer to you, it seems increasingly high-pitched, but then it moves away and it gets lower-pitched. This is because the sound waves are getting bunched up as the thing emitting them moves towards you, making them higher pitched, and they're more spread out as the thing moves away, making them lower pitched. When this happens with electromagnetic waves, including light, the light shifts blue when it's getting closer, and it shifts red when it's getting further away. Atoms emit certain, very specific wavelengths of light, so when we observe distant stars, the red shift or the blue shift can tell us quickly that they are moving towards us or away from us. When cosmologists observe that the universe is expanding because all the galaxies have a red shift, it also appears that expansion is speeding up because the further away a galaxy is, the faster it is going, even accounting for the additional time it takes for that light to get to us. Space is getting less dense. This is also what leads us to think that there was no one origin point of the Big Bang. Galaxies on all sides of us are moving away at the same speed relative to their distance from us. So unless Earth really is the center of the universe is expanding uniformly everywhere. This is like if you drew a bunch of dots on a balloon and then inflated it. The dots are all spreading apart from each other. There's no one place on the balloon that is exploding outwards, but rather everything was close together, and then everything is at the same time getting further apart from each other. Now, it's important to note that this expansion doesn't necessarily mean that the universe is getting bigger, just that it's getting less dense. If the universe is infinite, then it's not getting any bigger because it's still infinite. However, there is progressively more space in between objects. This is something like Hilbert's infinite hotel paradox, where guests in a full, infinite hotel each move to a room that is twice the number of their original room, creating infinitely more vacancies. The universe stays infinite, it just gets more space in between. More on the implications of real infinities and Hilbert's hotel soon. Now, one key thing about that cosmologists point to when arguments about verifiability or falsifiability of cosmological hypotheses arise is the cosmic background microwave radiation. This is the radiation that we can see if a telescope is pointed out at empty space. It is predicted by the Big Bang theory, but it was not predicted by the competing steady state theory. Because the prediction is that this microwave radiation emerged after the Big Bang when the universe cooled enough to become transparent. When it was first observed, that falsified the steady state theory of the universe. These rays are the first light that was emitted by the universe when it first went from being completely opaque to being transparent. This radiation gives us a snapshot of the universe a few 100,000 years after the Big Bang. It depicts that the universe was much more dense and much hotter at that point. Based on this, the fact that the universe is expanding now, and experiments done at very high temperatures in the Large Hadron Collider, we can speculate about the events in the universe before this radiation was emitted. But the further back in time we go, the worse our understanding is and the less confidence we should have. All right, moving backwards from now. When we look back into the timeline of the universe, the past looks much hotter and denser than things are now. Note that this timeline is not to scale. So here is a brief glimpse at the timeline. Let's look at each of these pieces in order, starting from the current day. So our solar system was formed about 4.6 billion years ago. The Milky Way, our galaxy, was formed fairly early in the universe's history, about 13.6 billion years ago. Many galaxies formed during this period and have continued to form since. This epoch is often called the galaxy epoch. The first stars formed about 13.68 billion years ago. The first stars were formed as loose helium and hydron atoms collected together, ending the so-called dark ages as these stars started to light up and engage in fusion. Some of these stars go supernova at this point, creating elements that are higher up on the periodic table. There's a period called the Dark Ages that happens from the emission of the cosmic background radiation up until the first formation of the stars. It's from about 370,000 years after the Big Bang to about 100 million years after. The cosmic dark ages are a period after the universe was a giant, very hot and dense blob, up until when early hydrogen and helium atoms started to form up into stars. It began when the universe became transparent instead of opaque, and it's marked at its beginning by the release of the cosmic background radiation. So, as the temperature drops below around 4,000 degrees Kelvin, the universe suddenly becomes transparent. This is because all of the protons and neutrons start collecting up the electrons. The cosmic background radiation is released as the universe first becomes transparent, as electrons become bound to protons and photons are emitted all in one blast to the universe. This moment is often called decoupling. The cosmic background radiation is a snapshot of this point in time. Our evidence for what happened prior to this is much weaker. But we have some suppositions. We think before this we had a blob of quarks that coalesced into protons and neutrons as the universe cools about 1 second after the Big Bang. What we can guess about this time is drawn from experiments with particle accelerators that create very hot temperatures which mimic the early universe at this time. Some theorize that one of the different forces, such as the strong nuclear force, may have differentiated itself around this time, and that was what caused this shift. Now, before this period, we have a period of inflation. The universe is inflating rapidly, faster than the speed of light, very quickly growing inside, often called the inflationary period. Prior to this, we don't fully understand what's going on. We don't understand this because we don't understand how gravity and quantum forces interact with each other. Because in most cases, gravity acts on very large scales and quantum forces act on very small scales. So we don't need to reconcile them. This is the point at which the universe, where things were so densely packed that we do need some kind of grand unifying theory that would explain how gravity and quantum forces are interacting with each other. We don't have one yet. Now, as noted, the further back we go, the less confident we can be. Even if we can reproduce these conditions in a lab, we can't know if the laws of physics would have operated in the same way in the early universe. There are also underdetermination issues all over the place, where many different hypotheses can explain the existing data that we have, making it challenging to determine what is correct. Some theorize that the Big Bang was the universe breaking off from another universe. Some claim it was the universe collapsing on itself and then expanding outwards again. Perhaps the universe has existed stably in a super hot, super dense state for a long time until one day something changed and it suddenly began expanding rapidly. Two more things to touch on about the Standard Model. Dark matter. There are a range of questions that the present theories leave unanswered. One of them is dark matter. We see parts of the universe where light is being warped, as if there were matter there that was exerting a gravitational pull. However, our systems, which can detect even matter which doesn't give off light, can't find anything there because it appears not to interact with light at all in this way. Some think dark matter is something left over from the formation of the universe, perhaps something that interacts with gravity but not with the other forces. Others think that it's another universe that's next to ours that's exerting influence. Others still think that our theories are just wrong, and just like the planet Vulcan, there's no such thing as dark matter, though this would likely require a paradigm shift to change our theories to account for these differences, just like we needed to change our theories to account for the perihelion in Mercury's orbit. Another concept that we're still trying to understand is sometimes called dark energy. This is the energy that is pulling the universe apart. We would think after the initial expansion, the pull of gravity would slow the universe down, possibly to a stop and possibly to even collapsing again. However, that's not what we're seeing. If anything, the universe is accelerating its expansion, though not as fast as it was in the inflationary period. Therefore, some have posited dark energy as a force that is driving the universe apart that we don't fully understand. As with dark matter, this could be described as something we do not observe, but need to exist for our formulas to work out right. So it's possible that it doesn't actually exist, and we're just misinterpreting the evidence we're getting from the cosmos, and we need new theories. Finally, some unjustifiable assumptions. While this is an interesting story, we might wonder if the evidence is sufficient to justify it. There are several tools that we're using to draw these conclusions, all of which rely on a range of assumptions. We'll look at several of these tools: looking back in time, redshifts, and cosmic background radiation. First, we have to claim that when you look into the sky, you're looking into the past. This faces the same objections as all of cosmology. Namely, it could be the case that there are different laws of physics in different parts of the universe, making light travel at different speeds than it does on or close to Earth. A similar case can be made against the idea of using redshift to assess movement of galaxies. It's possible that in other parts of the universe, chemicals give off slightly skewed spectra of information, or that there is some effect in between our galaxy and another one that's warping the light waves to make it appear that the galaxy is moving away, because it appears redder than it should be, when in fact it's some other phenomenon that's causing that, not a movement away, or not the same movement away we expect it to be. For the cosmic background radiation, this is often raised as a way that cosmology can actually act like a real science. Because it was predicted by the Big Bang Theory before it was discovered, this provides verification for this theory and falsification for its competitor. However, simply because it's consistent with the Big Bang Theory doesn't mean that this proves the theory, as there are many other theories that posit the same features of the universe. Okay. Now that we've talked a little bit about the science, let's talk about the religion and go into the cosmological argument. Something from nothing. So, a question which the Big Bang Theory does not address, though you might expect that it would, is how you get something from nothing. The key question of the cosmological argument for the existence of God. Now, while, as I argue in my series on the cosmological argument, the existence of God does not actually succeed in answering this question, it does ask an important question about how the universe began and why things are the way that they are instead of some other way. The Big Bang is consistent with many explanations of the origin of the universe, but it doesn't rule out a creator. It doesn't imply one or provide any evidence for one. It is possible the Big Bang was not even the beginning of our universe, but merely heralded a new stage in our universe. This is further evidence that cosmology suffers severely from the problem of underdetermination. There are many different theories that could explain the data, including the idea that God set off the Big Bang, but we can't distinguish between them. Note that some versions of the cosmological argument have more to do with possibility and necessity than kind of an initial temporal state. However, they are all focused on that initial moment of the universe. What caused the universe to be one way and not another? Next up, we're going to talk about a concept in cosmology called anthropic reasoning. This is the idea that we need to shift our expectations in terms of whether or not we have a biased sample. There are two key principles here, the Copernican principle and the anthropic principle. So, there are two principles used by cosmologists to estimate certain features of the universe. One is called the Copernican principle, which assumes that we are a normal observer. In other words, that we are not special and at a normal point in time and space. This is based on the claim that such special cases are rare, while the normal situation is much more common. We have noticed previously that some of the issues with this claim, the possibility that nowhere is fully normal, in other words, things look drastically different from every vantage point, the fact that this is just a fallacy of necessitation. If we don't assume this, we can't do cosmology, so of course cosmologists assert that it's true, and the possibility that our observations about the parameters are inaccurate. In other words, we are in a simulation, and the universe is actually much different than we think it is. But if that's not enough to make you doubt this absurd claim, here's a thought experiment. Imagine that you want to know what the opinions of everyone in New York City are about fashion, food, and music. You live in New York City, and according to the Copernican principle, you're likely an average individual. Therefore, whatever you think is what the typical New Yorker thinks. If you hate sushi, odds are everyone in New York hates sushi. If you love Weird Al, odds are everyone in New York does too, because you're probably a typical observer. If you wear shorts and a t-shirt to work every day, odds are that's what all New Yorkers do. It should be clear that this thought experiment leads us to a ridiculous conclusion. Just because one person picked out randomly is probably going to be in the middle of a distribution doesn't mean that they are going to be in the distribution or that they are representative of everyone in a population, especially when we're taking everything about that population as we are doing with the Earth, because that's the only point we can observe everything from. The problem here, as with the Copernican principle, is that a non-random sample of a single individual is never going to be representative. There's also evidence that cosmology is a pseudoscience. If the Copernican principle was false, we could never test it. We cannot observe the universe from anywhere but our little corner. And it's like someone doing an opinion survey without ever leaving their room by just thinking up what they think is true. Now, it's important to note, of course, we have sent telescopes and observation probes far out into our solar system and beyond, but even so, our solar system still counts as only a very, very, very small corner of the universe. Now, the other principle is the anthropic principle. This is the claim that the range of possibilities where we could find ourselves is limited by what we are, that there are certain points in time in the history of the universe where it's impossible to be a human observer. There are certain fundamental facts about the universe that, if they were different, humans would not exist. The anthropic principle argues we should take these into account when calculating our probability. Sometimes this anthropic principle is framed as having a weak version based around being required to be an observer on a planet that can sustain life, and a strong version that requires we are in a universe that can sustain life based on the cosmological constant and other constants within the universe. Another way of thinking of this is to say that this is a qualification of the Copernican principle. It says we should assume we are a typical observer out of the range of possible situations where an observer could exist. In other words, if the vast majority of places in the universe are such that they are inhospitable to life, we shouldn't assume that we are an average observer in any places in the universe, because most places in the universe do not admit of observers. We should assume that we are an average observer out of those places where observers could exist. This addresses issues that there could be a correlation between what we are observing and the fact that we are the type of thing that can observe. Such as if there's a particular type of gravity or interactions in areas that also happen to be better allowing of life. In other words, when calculating the likelihood of particular events, we should take into account the fact that simply by being an observer, we can only observe a subset of all events. One place this comes into play is when cosmologists calculate the push of dark energy to expanding the universe, the cosmological constant. Cosmologists calculate that the push of dark energy is very likely to be much greater than what we observe. This pushes against the Copernican principle, since it means that we're not in a normal situation, at least if our theories and calculations are correct. But the anthropic principle addresses this, since we are a normal observer, and universes with higher cosmological constants cannot have observers because they expand too fast for elements to combine and lead to situations where you could have life. So they argue that this is observation bias, because only in a universe with very little expansion due to dark energy could there be conditions that allow for life, and instead posit a near infinite multiverse to explain it, saying that there are many different universes, and we just happen to be in one of those universes that is allowing of life. This is once again a clear example of how cosmology isn't a real science. It is not falsifiable. The theory made predictions about the amount of energy and matter we would observe in the universe, and it was wrong. But instead of fixing the theory, instead of shifting our paradigm, cosmologists focus on positing more new, increasingly fantastical entities to explain more and more holes in the standard model of the universe by positing, oh no, let's talk about there being a multiverse. In fact, we're going to posit a very, very high number of universes to explain the fact that our numbers don't quite align up with what we're seeing in the world, instead of just admitting maybe our paradigm needs to shift. So there's some objections that we can have to these anthropic principles. This anthropic reasoning, the anthropic principle, and the Copernican principle. So these principles combine the worst of two separate, yet both epistemically sketchy fields: cosmology, much of which is arguably pseudoscience, and Bayesian epistemology, which tries to codify the degrees of confidence in particular statements through conditional probability. This kind of probability especially has issues with dealing with first-person perceptions of events and how that can impact your probability assignments. Check out our video on the Sleeping Beauty paradox for more on how this idea of a first-person assignment of probability can differ from the real probability out there in the world. This conflation of the epistemic situation we may find ourselves in, of this is likely because of who we are, and the likelihood of it actually existing out in the world, leads to this shaky abductive reasoning that we see in cosmology. Now, there are a range of issues with these two claims together as well. First, they rely on identifying an observer class. While this may seem straightforward, it is anything but. We do not know all the possible shapes and forms that life can take. We have only ever seen one example of life. Once again, a sample of one is not sufficient to draw conclusions. So making claims based on any possible observer is nonsense, since you don't know what the parameters for a possible observer could be. There could be observers that could exist in universes that have much, much higher cosmological constants. They might be observers that are very, very different from what we look like, but that doesn't mean that they're impossible. Just because you can't imagine it doesn't mean it's impossible. Now, this does lead to another piece of philosophy of religion closely connected to cosmology, the fine-tuning argument. Once again, cosmology veers into philosophy of religion with an argument called the fine-tuning argument. This is an argument about the physics constants in the universe. We have a full series on the cosmic fine-tuning argument, so check that out if you're curious, but we will touch on it briefly here. So, the argument basically claims that there are several constants, specific numbers that are used throughout the universe, which, if they were even slightly different, would mean that life in the universe is impossible. The argument claims that the only way that we could be so lucky as to be living in a universe with constants so finely tuned to life would be if there is a creator of the universe that designed it that way. In some ways, the intuition behind this argument is the same intuition behind the cosmological argument itself. It is asking the infinite why. Why is X a certain way? We can explain complex structures in biology with chemistry, we can explain complex structures in chemistry with physics, but at a certain point, there are certain laws of physics that we cannot explain why they are a certain way. They simply are that way. This argument says that because we can't yet explain why these constants are a certain way and not another way, therefore they could have been different. This is getting at the underlying argument of the original cosmological argument, this traditional argument of asking how we can get something actual from something that is merely contingent. Why is the universe one way and not another way? It is a certain way, and therefore there has to be some necessary being that created it that way. This is therefore a continuation of the long process of history where science explains things up to a certain point, but where science has yet to come up with the theories religion fills in. Now, we do have some responses to the cosmic fine-tuning argument. Like I said, check out my series for more, but here's a few of them. So, first, we can simply say that this idea of a probability distribution for the laws of the universe is a poorly formed concept because we have no real information about the real range of possible values. It could be the fact that these constants are logically necessary instead of merely nomically necessary. And we simply do not yet understand the math and theories that are required to prove that. If this were the case, saying that life would be impossible if these constants were otherwise would be like saying life would be impossible if a statement could be both true and false at the same time, or if pi was even a slightly different value. Sure, that might be the case, but those things being any different are logically impossible. It's also possible that there is a probabilistic range for these values, but that range is actually quite small, or at least it's quite small compared to the number itself. And it's very likely that they would be what they are. In other words, even if a tolerance to allow for life is within a 10 to the negative 100, it could be that the actual range of possible values only varies by 10 to the negative 1000. Some of what's going on here is this confusion of probabilities of us observing something and the probabilities of something being a certain way. In other words, committing the metaphysical horse fallacy. We are putting the epistemic cart before the metaphysical horse. We are basing our probabilities on what we can know or what we can understand as opposed to what actually could be. Just because we can state a probability based on what we could observe doesn't mean that that's the actual probability of something being set, or that what that thing being set is actually based on a probability at all. A third key intuition here is that the proponents of the fine-tuning argument have not proven that it is a probabilistic process that sets those constants. In fact, such a process seems to violate things like the principle of sufficient reason, which argues that there must be a reason that the world is one way and not another. Things that have seemed truly random have always been found to have a deterministic cause. Those things that seem probabilistic right now are likely just the things we have not yet come up with a sufficient explanation for. This directs us to a fourth response to the fine-tuning argument, that we simply have not discovered the theory which explains all of these constants, which unites them all under a grand unified theory. Thinking anthropically, we are likely not to be at the end of science. And all of our previous scientific theories have been replaced, proven wrong and replaced with new paradigms. So it's unlikely that we actually have the right paradigm right now, especially given all of the unobservable entities we need to posit to make this paradigm work. A fifth response is once again this issue of life as we know it, simply because the kind of life that we have on Earth could not be sustained in a universe with fundamentally different constants. It doesn't imply that another universe with different constants would not sustain a fundamentally different kind of life, perhaps at a drastically different scale given the rate of expansion. We certainly can't do any empirical testing of how a universe with different constants could actually behave, so while we might speculate that they would not be compatible with our life, we don't know that for a fact if there are any other kinds of life that cannot live here but could live under different conditions. The sixth response is popular among cosmologists, and it is the claim that our universe is but one universe in a giant multiverse of universes. In the same way that it may be unlikely that the Earth can sustain life, but there are so many planets we don't find it impractical. One way to explain these constants is to say that there is a multiverse of many universes that have different constants. Many cannot sustain life, but some can. What do you think? Is cosmology really a science or more of a philosophy? Do you think our explanation of the earliest moment of the universe are justified by the evidence we have? Does anthropic reasoning work, or is it a misunderstanding of probability? Leave your thoughts in the comments below. Watch this video and more here at Carneades.org, and stay skeptical, everybody.